In this section, we're going to take kind of a big change from what we've been doing so far, and we're going to be looking at linear correlation between data. To talk about this type of data, let's first of all give it a name. It's called bivariate data. It's called bivariate data because I have an x and a y value for each ordered pair. Now this is similar to what we've looked at in the last section with the matched pair designs, but we're doing something a little bit different with it in this section. So it's called bivariate data. Now with bivariate data, what I want to do is I want to plot the data, and the plot that we're plotting is called a scatter plot. And then the scatter plot, what I like to do is I like to plot on the x-axis and the y-axis each of these ordered pairs. Now as I plot these points, I'm looking to see if there's a linear correlation. So we're specifically looking at a linear correlation. Now if we look at the data set that we have here, we can see that I could very easily sketch a nice little line through here, so it does look like it has a linear correlation. And I would specifically say it has a strong positive linear correlation. Now the reason that we say it's positive is that the slope of the tangent line here, or the slope of this line, is positive, so this is a positive sloping line. Let's go ahead and look at another example. And for this example, we could look at, again, points that are plotted as x and y values, and we could look to see how they're correlated. And here we can see that we have another set of points that look fairly linear, and this one has a strong, and the reason I say strong is the pattern is definitely linear. It's tightly clustered about the line. This has a negative correlation though. And again, it's still linear. Now the reason we say it has a negative correlation is the slope of this line is negative. Now data sets can be very correlated. Correlated means related, but they don't have to be necessarily linearly correlated. So for instance, this graph is definitely not linear correlated. This is a curved, kind of a quadratic relationship. So this is a very weak linear relationship. It looks like to me it's a very strong quadratic relationship, but we're looking at linear relationships. And we could also have data sets that aren't correlated at all. For instance, I could be looking at this data set, and I would have to say this has no linear correlation. Or we could even say weak. If I try to draw a line through here, it seems like I have a lot of options. I have this line, I have another here, another that could be here. There's just not one best fit line here. And so what ends up happening, they all average down to this horizontal one usually. Now over here one more time, there is a strong relationship. It's a quadratic relationship, but we're specifically looking at only linear relationships. Now from this bivariate data, not only can I create a scatter plot, but I can come up with a measurement that quantifies the strength of the linear relationship. So the correlation coefficient is a numerical value that gives us the strength of the linear relationship. Now the word linear is important here because it doesn't talk about any other type of relationship like a quadratic, etc. So if you were to put a line of best fit through here, it'd probably just give you, a horizontal line through here, and you're going to get something about the correlation coefficient. So you always have to take into account the correlation coefficient with the picture of the scatter plot. So again, strength of the linear relationship. So correlation coefficient. Let's go ahead and look at some other characteristics. First of all, the correlation coefficient is denoted with a lowercase r. This lowercase r value, so r is the linear correlation coefficient. Again, this gives us the strength of the linear relationship. So it's a linear correlation coefficient for a sample, and this is the important word here, for a sample of paired data. Now, because this is based on a sample, it's doing its best to estimate the correlation coefficient for a population, and this is represented by the Greek letter rho. So this is the linear correlation coefficient for a sample. Sorry, not a sample, for a population of paired data. So these are identical. One is based on a sample, one is based on a population, and so that's the big key word here. So that's another thing that we can use when we're talking about the correlation coefficient. The strength of the linear relationship, R, is based on a sample, rho is based on a population. Now, another important characteristic of the linear correlation coefficient, R, is it's always between -1 and 1. So again, this means between. Now, 1 would be a perfect positive linear correlation. -1 would be a perfect negative linear correlation. Now, of course, there's all sorts of numbers in between as well. So we could have like 0.95, which would be a strong linear correlation coefficient that's positive. We could have 0.2, which is a very weak positive linear correlation coefficient. And then, of course, we'd have 0 right in the middle. And 0 in the middle would mean there's absolutely no linear correlation between the variables. Now, we need to keep something in mind. We keep talking about correlation. This is very important to remember. Correlation does not imply causation. So we have to be careful when we're working here. Just because we find that two things are related, it doesn't mean that one causes the other. So this is a very important idea. Correlation does not imply causation, and we'll talk about this quite a bit. Now, when we're trying to test to see if the correlation coefficient is equal to 0 or not equal to 0, we'd go ahead and start with our hypothesis test. So let's go ahead and look at our steps for hypothesis testing. And we can use a p-value test, and then we can also use the critical value test as well. So the critical value would be the traditional approach. So for this one, let's go ahead and look at the traditional approach, and with the traditional approach, this is when we use critical values. Now, if we're going to use critical values, we need a table. Our calculators don't give us values from the table, so we need actually a sheet of values. So if you log into MyMathLab, and down the left-hand side here, you have the option to go into tables. The tables that you're going to want to use are right here, critical values of the linear correlation coefficient R. And if you click on that, we're going to have a list. It's a much smaller set of tables than we're usually used to with the normal and the t. And you can see that on the left-hand column, we just look at sample size, and then they chose two common values of alpha, and alpha values are 0.05 and 0.01, and then these are the critical values. And so we're going to be referring to this table throughout this homework set. So I will bring a copy of these tables to class, a copy for you guys to keep, and then there's also an extra copy here if you want to look while you're working. Okay, so first thing that we're going to do for the traditional or the critical value approach is to state HO and HA. Now, stating HO and HA is going to be pretty straightforward because they don't really ever change for the correlation coefficient test. So what we always use here is rho, because that is our population correlation coefficient. We use rho equals 0 versus the alternative, rho not equals 0. Now, rho equals 0, we can translate as there is no linear correlation. Now our second option here, row not equal to 0, that means there is a linear correlation. Now it doesn't tell what that linear correlation is, but it says there is one. They are related some way. So that's step 1. Step 2 is to go ahead and state the level of significance. And this is usually given to you in the problem. Remember, this is our value of alpha. Step 3, based on this level of significance, we're going to go ahead and determine the critical values. Now the critical values that we're going to use are from our table. And to use this table, we need to know two things. We need to know our sample size and we need to know alpha. Okay, number 4 is we're going to go ahead and calculate a test statistic. Now this test statistic, we don't really want to go after the formula. We're going to use your calculator. And I'll show you how to do this. Then we're going to have to make some sort of a decision. Okay, so this is how the decision works. If the absolute value of R, okay, and so up here when we determine the critical value, we're going to take this value of R that we calculated with the test statistic and compare it to the critical value. So again, that calculate the test statistic, this is basically your value of R that we can talk about. Make this look a little better. That's your correlation coefficient. If the absolute value of R is greater than your critical value, then we would make the decision to reject the null hypothesis. And that's HO. So we would reject HO or reject the null hypothesis. And then from here, then we would conclude that there is sufficient evidence to support the claim of a linear correlation. Okay, so now our other case then would be if the absolute value of R was less than or equal to our critical value. Then here, we'd fail to reject the null hypothesis. So fail to reject HO. And then here we would conclude that there is not sufficient evidence to support the claim of a linear correlation. So that's our quick little rule here. And really, this is no different than the critical values that we talked about before in our other methods. So basically what we have here then is we have this curve and we have some sort of a critical value here and another critical value here. And then our test statistic, if it falls in this region, would be fail to reject. And if it falls out here, these are called our critical regions. This is where we would reject HO. And this is where we would reject HO. Okay, so if we had, let's say, critical values of 1.234 and negative 1.234, and our correlation coefficient was something like, well, I guess our critical values wouldn't be clear up to 1 because the largest our correlation coefficient can be is 1. So let's change these just to be consistent. If I had my correlation coefficient out here, let's say at positive 0.897, and then down here at negative 0.897. And then my correlation coefficient R was, let's say right here, the absolute value of R, I'd fail to reject. But if my absolute value of R was out here, then I would reject HO. So those are the things that I'm looking at. So this is my step where I make a decision. And then our last step, of course, is to summarize. And again, we always blame it on the data. The data supports the conclusion, or the data does not support the conclusion that there is enough evidence to claim a relationship of a linear correlation or not. We kind of have the summary up here a little bit too. So that's the traditional approach. Let's go ahead and look at hypothesis testing with the p-value approach as well. And we're going to use our calculators to help us calculate our test statistic and everything. So our first step here would be to state the null and the alternative hypothesis. So again, we're using rho equals 0 versus rho not equal to 0. So this example for rho equals 0 is basically stating that there is not a linear correlation. And the second step here would be if rho does not equal 0, we would be trying to test to see if there is a linear correlation. Second step is to state the level of significance. And that's alpha. It's usually given to you. Next thing we're going to do is we're going to calculate the test statistic. And in this case, this is always going to be my value of R, sample correlation coefficient. We're going to calculate the p-value. We're going to make a decision. Now for my decision, if p is less than or equal to alpha, we'll reject HO, so this is not any different than everything else we've been doing in the last few sections. And if p is greater than alpha, we'll fail to reject HO. And then of course, the sixth step, we will summarize. Okay, so let's go ahead, now that we know kind of all the rules that are in place, let's go ahead and just start looking at some problems to see how we can tie all of these together. Now we're going to be using our calculators quite a bit to first of all look at a scatter plot. It's important to look at a scatter plot first to see if it's even reasonable to assume some sort of a linear correlation. So for our first example, let's go ahead and look at heights and pulse rates. So let's suppose a sample of 10 women were measured for their height and pulse rate. And after we went through and we calculated these with our calculator, we found out that R is going to be equal to 0.721. Now this value of R, that's our sample linear correlation coefficient. So this is pretty close to 1. And because it's pretty close to 1, it kind of implies that there's a fairly strong linear correlation between the variables of height and pulse rate. So what we want to do is we want to determine if there's sufficient evidence to support the claim that there's a linear correlation between height and pulse rate. So let's go ahead and go through the steps. Let's go ahead and use a value of alpha here of 0.05, and I'm going to use the traditional approach here. So this is my critical value approach. So HO and HA. So rho equals 0 versus rho not equals 0. There is no linear relationship. and there is a linear relationship. Okay, so those are our two HO and HA, those will not change. Alpha would be 0.05, and our third step is go ahead and determine our critical values. Now to determine the critical values, we'll need to go ahead and use the table that we were looking at earlier in my math lab. Okay, so we had 10 women and we have an alpha of 0.05. So here's 10 women, here's alpha equals 0.05, so our linear correlation coefficient, our critical value would be 0.632. Let's go ahead and take a screenshot of that. And again, we just really need the first one. I'll pull the full value in from our table. Okay, and then again, we have a sample of size 10. We're looking at alpha equal 0.05, and then we can see that these basically converge right here at 0.632. So we're basically, because it's a two-tailed test, we're looking at critical values of plus or minus 0.632. Okay, next we'll go ahead and calculate our test statistic, and that was actually given to us already in the problem. So up above it was given us as 0.721, and then we're going to go ahead and make a decision. Now remember, to make a decision we look at the absolute value of R. So the absolute value of 0.721, that's going to be is greater than our critical value, 0.632. Okay, and because it's greater than the critical value, this would imply that we'd failed to reject HO. And then for our summary, we'd have to say something like, whoops, I have a mistake here. Because 0.721 absolute value is greater than 0.632, we would reject HO. Be careful about that. And let's go back up and look at that real quick, where that rule is. We reject HO. Now that's going to be up here. The absolute value of my correlation coefficient for the sample is greater than the critical value, you would reject HO. Okay, so that's why we change this to reject HO. So we'd have to basically say that there is sufficient evidence to support the claim that there is a linear relationship or a linear correlation. And the two variables that we were looking at here were height and pulse rates. Now something interesting, that doesn't mean that height causes a higher pulse rate or pulse rates cause a particular height. We can't establish causation, we can just establish correlation. Now there might be a reason, a physiological reason for this relationship, but this doesn't answer that question. This just says there is some sort of correlation right now. So that's an example of using your critical value approach when you're finding these values. Now the next problem that we're going to do, we're going to be working with a set of raw data, and from the set of raw data we'll learn to calculate, or actually create a scatter plot, calculate correlation coefficient, and find a p-value for the hypothesis test. So for this one, we're going to be using the p-value approach. And we're just going to be given some raw data instead of being given our correlation coefficient right away. So this is our raw data. Now remember, the x and the y values are matched pairs in a sense. They're bivariate data. So for each value of x, I have a corresponding value of y, and I want to think about these as ordered pairs. So this is our raw data. Now we'll go ahead and put this into our calculators under the list command, but we won't be taking a difference or anything like we did in the previous section. Now, if we're going to use the p-value approach, the first thing I want to do is I want to state my HO and HA. Now, you could do a less than, greater than correlation coefficient connection. So we're going to take the not equal to case, and we'll note that in the calculator when we do this test, but you could do a positive correlation would be greater than 0, a negative correlation would be less than 0. Let's go ahead and use a level of significance here of 5%. So alpha equals 0.05. Now to get started, the first thing we should probably do is to look at this and determine whether we even think it's reasonable to say that there's a linear correlation. So let's go ahead and go to Stat, Edit. Let's go ahead and clear out both my lists, and if you have other lists, you can clear yours out as well. And let's go ahead and enter the data. So for my x values, I had 47216. So 47216. Now we want the corresponding value with 4, which was 8. So we have to put these in the same order. So 8, 12, 5, 3, 11. Okay, now we want to take this and we want to create a scatter plot to see if it even looks reasonable to be linear. So we want to go to stat plot, which is second y equal. You can see the word stat plot above here. Go ahead and hit enter on the first stat plot, and we want to turn this on. And the first option here for me is a scatter plot. Now my x list was L1 and my y list was L2. So if we want to note that, we can. So we can call this L1 and L2 just to help us keep track. And this is actually going to go through and calculate a t-statistic for me after we do our scatter plot by using the test feature. And then we'll hit graph. So I'm looking at this now. If nothing shows up on your window, make sure you remember that you can go to zoom, and this option 9 for mine is zoom stat. So if we choose zoom stat, usually it will pull in these values. Now this looks very linear, so I think it's probably a good idea to run this test to see what the linear correlation coefficient is. It looks like to me that it's a very strong positive linear correlation. Okay, so the points appear to have a straight line pattern, so it appears to be reasonable to suggest there is a linear correlation. Okay, next step. We have all the data entered in our calculator. Let's go ahead and turn off our stat plots, because if you have stat plots on, a lot of times that causes some problems with your regular plot. So it's always a good idea to go in and turn that off. Now we go to Stat, Tests, and we want to scroll up or down, either one, and we want to go to the linear regression t-test. This is the linear regression t-interval. We want to go to the linear regression t-test. And what we want to do then is on the x list, we want to say what our x variable is and what our y variable is. And we can see from over here, x was L1 and y was L2. The frequency just means how often they occur, and we're checking the not equal to case. Now this one where it says regression equation, we don't really want to worry about that right now, but basically it tells me the line that fits through there best, and then hit calculate. Now we have a lot of information here. First of all, we can ignore some of this. This t-value seems to be pretty interesting. It's a very, very large t-value. And this also gives me a p-value here. Now it's not 1.54, it's 1.549 times 10 to the negative 4. Degrees of freedom are 3. And if you notice here, I have a 5 paired sample. Degrees of freedom are n-2, but we're just letting the calculator take care of that for us. And then finally we come to this value of r, and this value of r is really what I want to be able to see. So r is 0.997, that's huge, it's very, very close to 1. let's go ahead and take 2 screenshots of the first half of the output from the calculator and then the second half as well. Now there's a couple things that we'll want to keep track of here. Our test statistic, which in this case is t, and we'll go back and amend some of our notes for the p-value as well. And the test statistic you can go through and calculate, but really it's probably just a good idea to use your calculator output because again the formulas get to be a bit much. Okay, so step 3 would be to go ahead and calculate our test statistic. Now for the critical value approach, we just used R. For our test statistic here, let's go ahead and look at 24.187. That's a huge test statistic. Now up here, when we look at our p-value approach, p-value approach, here we calculate our test statistic. And this test statistic is based on R like we said, and our test statistic is equal to R, once we have it calculated, over the square root of 1 minus R squared all over n minus 2. And again, I don't expect that you'll have this memorized. We're just going to use our calculators to help us with this. So that's our test statistic. Number 4 is our p-value. And our p-value here is given. And it's basically 1.55 times 10 to the negative 4. So if I move this back 4 places, p would be approximately equal to 0 really. I'm going to write this as 0.00015. Okay, but approximately equal to 0 for all intents and purposes. Okay, number 5, we're going to make a decision. And then we're back to the good old rules here. P less than or equal to alpha. My value of P, 0.00015. My value of alpha was 0.05, 5% level of significance. Again, P is less than or equal to alpha, therefore we reject HO. Okay, so reject HO. Then we have a conclusion. Now, if we reject HO, let's go back and look at what HO is. If we reject this, what we're saying is the correlation coefficient is not equal to 0. So that means we have some sort of a linear relationship. So what we could say here then, based on this conclusion, is that the data supports the conclusion that there is a linear relationship between x and y. And usually we'd want to say what those variables are, but in this case they didn't give us what x and y meant. They just said between x and y. Now if you were asked to use the critical value approach to this, then what you would do is you would go off of my R value and compare that to the critical values from the table that is in my math lab. So this is the sample correlation coefficient that's given. So whether you're asked to use the p-value approach or the traditional approach, you're always going to go back and use this linear regression t-test to get your information. So this is your sample correlation coefficient. Okay, so again on this one, the data supports a conclusion that there is a linear correlation, and we can't say just that there's a correlation or a relationship. We have to say that it's linear because this is a specific test to test for linear correlation. For the next problem that we're going to be looking at, they're not going to give us a data set, but they're going to just give us a graph. And then based on the graph, we should be able to create our own data set and then talk about whether a linear relationship seems reasonable or not. So let's go ahead and make this graph a little smaller first of all. Now if we look at this graph, the first thing I want to know is to determine whether there appears to be a linear relationship or a linear correlation or not. And then I want to find the value of the correlation coefficient. And then we want to test to see if there's an actually statistical relationship or a strong statistical relationship between the correlation coefficients of these variables. So first of all, if I want to calculate the correlation coefficient, I need to know what these ordered pairs are. So we need to know what x and y are. And it's not too bad to figure that out because this is a pretty nice little graph. But if we look at x, this seems to be x equal 2, and this seems to be y equal 10. So that's the ordered pair 2, 10. Now over here, this column has all values of x equal to 8. This one is 9 and 10. So I have 3 values with x equal 8, 3 values with x equal 9, and 3 values where x equal 10. Now my values for y for these values are going to be 1, 2, and 3. So I have 1, 2, 3. For my y values I have 9, 1, 9, 2, 9, 3, 10, 1, 10, 2, 10, 3. So the first question to ask is, based on the graph that we have right now, including all of these 9 points and this point as well, does there seem to be a linear correlation or a strong correlation of some sort between the two values? And I would have to say yes. There is a strong correlation between x and y. Now if we had to draw a value in here, we could go ahead and say, well, this point is so influential. If I just looked at these points down here, I'd have to say there's no correlation whatsoever. But with this point up here, it takes my line and jerks it right up from a horizontal spot to here. So that's why I would think that there's a strong linear correlation. Okay, but we'll let the numbers calculate that for us. So the next step I want to do is to find the value of the correlation coefficient. So let's go ahead and calculate the correlation coefficient. And we're going to use our calculator to help us do this. And these are the data points that we'll use for that. So we want to go straight into Stat, Edit. We want to go to my L1 and my L2. And of course, we want to clear those out. So under L1, we'd have 2, and then 888, 999, and then 10, 10, 10. And then our values for the corresponding, we need to make sure they're entered as ordered pairs. 2 went with 10. And then I had 1, 2, 3 for my 8s, 1, 2, 3 for my y's, and 1, 2, 3 for my 10s. Okay, now to calculate my correlation coefficient, there's quite a few different ways that I could do this. But I think the easiest way is to go into Stat, Tests. And again, I want to go into Linear Regression t-test. Now we're going to test the not equal to case because we want to see whether a correlation exists or not. So that's L1 and L2. So if we want to make that note over here, this would be L1 and L2. And again, we're doing a formal hypothesis test. But right now I just want to go ahead and check and see what that value for R is. So I'm doing the not equal to case. That's, is there a relationship versus there is not a relationship. And I want to scroll down just a little bit to get to that value of R. So here's that value of R that I'm looking for. So here is my p-value. Here's my test statistic and my degrees of freedom. Well, like I said, for now we just want R because we're going to use the traditional approach on this. And for the traditional approach, we don't use the value for our correlation coefficient or we don't use a p-value. We could though. You could look at that and find your p-value. But let's just go ahead and stick with our traditional approach. So here's R. So our value of r is equal to negative 0.8929. And just make sure you read the directions to see how they're correlated. So my next question is there a correlation between x and y? Now we want to go ahead and use the traditional critical value approach. Now you can also use the p-value approach. And if you want to use the p-value approach, remember your p-value is just a little bit higher up on your list with the calculator. So we're going to go through all the steps. 1, HO versus HA. Rho equals 0 versus rho not equal to 0. So rho equals 0 is no linear relationship or no linear correlation. And then of course rho not equal to 0 would be there is a linear correlation. Step 2 is alpha, and for alpha let's go ahead and use the 1% level of significance. Step 3, let's go ahead and calculate our critical value. Two-tailed test, so I'll have 2 critical values. Now remember, this is from our tables in my math lab. So let's see if we can figure out what those tables have in them. We would go to tables, linear correlation coefficient. Looks like I have too many windows open here. Okay, let's see if it'll let us do it now. Critical values for the linear correlation coefficient. Now, if you look at all of our data points, I had 10 for my data points. I had 10 of them, and we're looking at alpha equals 0.01. So my critical values would be 0.765. So let's take a quick shot of that so we know where those critical values come from. So again, we have a sample size of 10 pairs. So if you wanted to count these, you could, but we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I come down here, and I have n equal 10, and I have alpha equal 0.01, so 0.765. Okay, now next I calculate my value for my test statistic. Now for the critical value approach, so test statistic, for my critical value approach, my test statistic is just my R value. And my R value is negative 0.8929. And then I make some sort of a decision. And to make my decision, I take the absolute value of R, and I say the absolute value of R is going to be more extreme or greater than 0.765. So the absolute value is going to be a positive 0.8929 is greater than 0.765. And so what I'm going to do here is I'm going to go ahead and reject HO. And the reason I'm going to reject HO is that the correlation coefficient, R, is in the critical region. And when I say it's in the critical region, what I'm referring to is it's more extreme than my critical values. Okay, so that's my decision. And then of course we'll have a summary. And for my summary, basically what we're going to say here then is there does appear to be a linear correlation. The data supports a linear correlation between X and Y. Now the interesting thing about this is that linear correlation, negative 0.8929, that is very, very close to -1. And so that's telling me it's a pretty strong linear correlation. Okay, now, second part to the same problem. Same problem, second part. So what they want us to do for the second part is they want to take that same exact graph that we were just working with. So let's see if I can find that same exact graph up here. Okay. So same exact graph. And they want us to throw out that outlier point and then see how that changes everything. So if we throw out this outlier point, basically they're saying get rid of this one because it's not where the others are. And then I'm going to have a value of X and Y that I'm going to work with. So my values would be 888, 999, and 10, 10, 10. So we're going to see what's going on with this point because it kind of seems like an outlier. It's not clustered around all the other data points. So if I throw out the outlier, what's happening? Now we already have this data in our calculators. Let's see if we can just throw out one data point. Now the data point that we don't want, let's go ahead and hit edit here, was this point of 210. And I think if we turn these to zeros, that's not going to be good. We don't want to do that. So let's go ahead and just go up and clear these. There probably is an easier way to do that, but I think it's going to be easier just for me to type these in and start over because they're pretty easy data points. 888, 999, and 10, 10, 10. Okay, and then over here we have 1, 2, 3 that goes across from each value of 8, each value of 9, and each value of 10. Okay, so now they want us to say, okay, what is the new correlation coefficient? How is that changed based on throwing out that one outlier? Does that outlier really have any influence? So we go to linear regression t-test, and I basically want to look at my correlation coefficient. My X and Y list are still L1 and L2. I'm still looking at a two-tailed test. And now when we go through here, look at our t-value, it's really changed. And look at our correlation coefficient, it's 0. So that is a huge change. Remember the correlation coefficient before was negative 0.89, which is a strong negative linear relationship. Now this has changed, completely changed a lot down to r equals 0. So I think we have pretty strong evidence right here to say that there is no correlation between the two variables x and y when I throw out that outlier. So that outlier is a very influential point. So I could go back through and I could go ahead and test the hypothesis test using the critical region, etc. But for here I can see that r equals 0. So I think eventually what I'm going to get to when I run my hypothesis test is fail to reject HO. And when I fail to reject HO, that's going to tell me there is not a linear correlation between the random variables x and y if I throw out this outlier point. Okay, so those are the things that we want to look at here when we run into these. So a couple of important things. Correlation does not imply causation. X doesn't cause y, y doesn't cause x. And we want to really use our calculators a lot for these calculations because they do get pretty ugly. As usual, if you have questions, please bring them to class. Stop by my office, or you're welcome to use the Math Center as well. Good luck.